Hey, I have here another integral on the board. We have the integral of 6 sine x plus 5 cos x over 4 sine x plus cos x dx. And some of you may notice that I did an integral like this not long ago at all, maybe a week or so back, and it was very similar to this. There was a few interesting comments from Linus and Adandap with a completely different method. What I wanted to do is just do another one of these problems and using their method just so that everyone could see how it works. Okay, so to start with, I want to give kind of the general idea of what we're doing here. And the idea is we're going to put this integral into a totally different form. What we want to do is get the integral into this form where it's going to be hopefully easier to work with. We're actually changing the angle here by some value, and we'll have a different value for the numerator and denominator. But we can actually find out what this is and what this is going to be using our values from the integral and using kind of the angle sum formulas in reverse. Okay, so we'll look at our general angle sum formula for sine here. This will allow us to transform something in the form sine of a plus b. And then we notice over here our sine of x plus t and x plus theta, that's in exactly this form. So let's just look if we have, and let's just include the r in there, we'll just distribute that in. So if we have r1 sine x plus t, and we just want to use this formula, and what I want to do is just kind of equate this to my denominator here. So like, we're going to have, this is going to be 4 sine x, and this is going to be just a plus, we'll write a 1 there for cos x. That tells me that r1 sine t is going to be equal to 1, and then grouping this, r1 and cos t is going to be equal to 4. And what I can do is just set this up as kind of a ratio. My r1 sine t value is just 1, my r1 cos t value is 4. So with some quick simplification, by canceling the r1, we just find that tan of t equals 1/4. And then with that, I can just kind of draw my triangle just like we were doing like a trig sub or something. We'll draw the triangle, we'll draw a right triangle with the angle t. If tan t is 1/4, we can write our sides as 1/4. Opposite over adjacent is going to be 1/4, and then we can calculate our hypotenuse. Using Pythagorean theorem, we find that 1 squared plus 4 squared equals square root of 17 squared. And while I'm here, I just want to kind of isolate my value for sine t and cos t. So sine t is just going to be opposite over hypotenuse, so that's going to be 1 over square root of 17. And then for cosine, adjacent over hypotenuse is going to be 4 over square root of 17. And then with that, you can just get your r1 value, and notice r1 has to be square root of 17. Just confirming it, you can just validate that r1 sine t gives us back our 1 value if you multiply that out, and the same thing with our r1 times cos t value. If you multiply that, it'll give you 4. Okay, now I've captured those values over here on the right, so we don't forget those. And now we're going to do basically the exact same thing for the numerator. Basically the exact same thing with this formula here, just instead of having a t, we're going to have our theta here, and we'll equate that to our numerator. So our numerator is going to be 6 sine x plus, then we're going to have a 5 cos x, and so then we can say r2 sine theta is 5, r2 cos theta is going to be 6. Again, exactly the same way, we'll create a ratio here of r2 and, r2 sine theta and r2 cosine theta. Then, let's see, so r2 sine theta is 5, r2 cos theta is 6. So this means that our tan of theta is going to be 5 over 6. So then looking at our right triangle, if tan of theta is 5 over 6, we have these sides. We can calculate with the Pythagorean theorem that our hypotenuse must be the square root of 61. And I'll just find my sine of theta, which is going to be opposite over hypotenuse, so that's going to be 5 over square root of 61. And then we'll get cosine, which is going to be just 6 over square root of 61. And the same thing we did previously, because we know that r2 sine theta is going to be just 5, we can say that r2 must be square root of 61. Okay, now at this point, I think we have everything we need over here on the right in order to finish this off. So what we're going to do to continue is we're going to use this formula like I mentioned. But now notice r2 over r1, that's just going to be a constant value that we can bring out front, and we know those values. So what I'm going to do is take out front of the integral, we're going to have square root of 61, and r1 is going to be square root of 17. And then let's just write out the rest of this integral. So we have that. Anyway, I'm not sure if I mentioned at the beginning of the video, this is a new method to me. So I had never done it before, and the first time I did it, I was stuck at this point because I didn't quite know, what do we do with this? We can't just cancel the signs. That would be nice if this was 1, but we've got different angles. So reading the comments in that previous video, there was a trick from Linus, and I can show you that. What he did was, in the numerator, he just rewrote this angle. Let's just see. if we write this as the sum of two angles, notice if you add these all together, the t's will cancel and you're back to x plus theta. So this value is actually exactly the same as this, but writing this in this form allows us to use the angle sum formula again. So let's take a look at how that's going to look. So using that angle sum formula, we're able to break it out this way. And of course, we've got a much longer expression and it looks more complicated, but this is going to allow us to split it into two integrals. But when we split it into two integrals this way, now we get a cancellation here. This term right here is going to be just, this term here is going to be cotangent, so we can deal with this. This value and this value is going to be constant, so let's rewrite this and see what we have. Okay, so again, we just have constant values right here outside of the integral, of course including the square root too. But both these integrals are very easy to deal with right now. So this integral is just going to be x, so we can rewrite this part. So integrating this, we're just going to get x. Then dealing with this second integral, what I'll do is we'll do an informal u substitution. We don't really need to write this up because it's pretty clear that if we make our u the denominator, sine of x plus t, the derivative of sine x plus t is just going to be cosine x plus t dx. So when we integrate this, we're just going to end up with a natural log of sine x plus t. And at this point, we're really close. We just need to figure out what is this value, and this value. And what I'll do is start with sine x plus t, because we really determined that initially. And r1 is square root of 17. So what we're saying here is square root of 17 sine x plus t is the whole denominator, which is for sine x plus cos x. Now we could divide both sides, a square root of 17. But notice we have a natural log around this. So when we split this out by the log properties, we can write it like we're subtracting. We could split it out this way. But doing that, this natural log 17 is a constant term, and this is going to get absorbed in the constant. So what I'm going to do instead is we're going to ignore this piece, and we're just going to use 4 sine x plus cos x. Okay, now I'm going to look at cosine theta minus t. What we'll do is use the angle difference formula here. But then when you do that, you'll notice we have every value we need over here. We already got these over here on the right. Let's plug in all these values from the right and see what we have. And then from here, now that we have all these values, we just need to multiply it out and add. We can see the denominator is going to be square root of 61 times 17. I'm not going to simplify it right now. And then here we have 24 plus 5, 29. And then next we'll look at this sine theta minus t value and do the exact same thing. When we use the angle difference formula for sine, we get this. Then again, we'll just take all our values from the right and plug in. And when we do that, again, we're going to have here 5 times 4 is 20 minus 6. This is going to give us 14 over square root of 61 times 17. But then all that's left is just to multiply this in to finish it off. So what's going to happen here is like square root of 61 is going to cancel here, and then square root of 17 times square root of 17 is going to give 17. So here we're going to have 29 over 17 x plus something really similar here, 61, square root of 61 is going to cancel, and we're going to end up with 14 over 17. Our natural log expression, again, we discarded the denominator here, and so we're just going to say absolute value 4 sine x plus cos x. I'll add a plus c, and that's it, we're done. Again, thanks again to Linus. I thought it was a really interesting method. Enjoyed doing this one. I'll provide a link in the description to the other videos so you can check that out. Thanks again for watching. Have a great day.